On the test you guys just got back, I think we did pretty good overall, but I want to remark about a couple things about hypothesis. What's something that your null hypothesis should always contain? There's two things that I'm looking for. Yeah, the possibility of equality. So you should have a less than or equal to, or greater than or equal to. There's one other thing that I'm looking for in my null hypothesis, the statement of that null hypothesis. What is it? Yeah, your parameters. So what are our parameters? Christine gave us parameters. What are the parameters that we've tested so far? Mu, sigma, and p. Those should be part of your null hypothesis and your alternative hypothesis. What I shouldn't see are things like x bar, s, and p hat. What are these in comparison to these? Yeah, those are statistics. So your null hypothesis always tests claims about parameters. Those should be in your null hypothesis. And in your alternative hypothesis, you're going to have the opposite of this, but you're never going to have statements regarding statistics. We're not testing claims with statistics. We are about statistics. We test claims with statistics. We use statistics to test our claims, but it should have one of these three. Now, speaking of these three, in Chapter 8, we tested claims about the mean, the standard deviation, and the population proportion. That was for one population. In Chapter 9, we started this in Section 9.1. We started testing claims about two population proportions. So, two population proportions. That was 9.1. We're going to continue that trend in Chapter 9 that we're going to test claims about two population parameters. So, today we're going to spend our time on testing claims about a population mean, except there's going to be two different cases. There's going to be the dependent case and the independent case for two population means. So two population means, and like I said, there's going to be the dependent case and the independent case. So the independent case is what we're going to work on first here. And the dependent case, that's going to be Section 9.3. So 9.2 and 9.3. There's going to be some assumptions that we're going to have to make for testing things in the independent case and the dependent case. But let's look at both of those right now. So for the independent case, we're going to assume that our two samples are independent of each other, and then the underlying populations are, again, independent. What does it mean for something to be independent? Something is independent of something else. It stands on its own. And in terms of statistics, like when we were thinking about probability, the outcome of one event doesn't affect the probability of the outcome of the next event. They're independent. Whatever happens with one has nothing to do with what happens with the other one. So, okay. So independent, we are going to assume that we have independent samples. That's the big assumption to start with. That's going to be the difference between Section 9.2 and Section 9.3. And one of these two things have to be true. Either we have large samples, and that is N1 and N2 are both greater than or equal to 30, or we assume that both of our populations are normally distributed. So, or assume both populations, or both populations are normally distributed. Okay, so a couple assumptions that we're going to have to make here. Probably one that I should write down, even though I don't typically mention this, and that is sigma 1 and sigma 2 are both unknown. Now, why would I have to write that down? Well, there is a test that you can do if you know the standard deviations, but these are population standard deviations, and it always felt unlikely to me that you would somehow know the standard deviations but not know the mean. I mean, remember, our hypothesis test is going to be something to the effect that mu1 equals mu2. That's our hypothesis test. If we're testing this, means we don't know these. How would we not know the means but somehow know the standard deviations? And a buddy of mine mentioned the example of the SAT scores. A lot of times the standard deviations will change from one year, or no, the standard deviations will be the same from one year to the next, but the means will change. Yeah, maybe. I don't know. In any case, it's not a big stretch to say that typically speaking, these things aren't known. So let's actually apply that to some problems here. And it's going to start with example A here. Well, example A, yeah. I guess I didn't write example A, but this is example A. And it's going to refer to weights of cans of Diet Coke versus regular Coke. When these come from the book, a lot of times they take out some of the fun stuff. These are cans of Coke. It says, assume the two samples are independent simple random samples from normally distributed populations. Great, that's checking off our boxes right here. Independent samples. I should probably also put SRS, simple random samples, as well. That's not something I emphasize because it's typically beyond our means to check that. So we got simple random samples that are normally distributed. Assume that the samples, do not assume that the standard deviations are equal. All right, I'll talk about that when we get to StatDisk. Complete parts A and B below. Use a 1% significance level for both parts. Test the claim that the cans of Diet Coke have the same weights or have weights with a mean that is less than the mean for regular Coke. Now, they actually define things for us here. You've got your Diet Coke here. That data represents population 1. And then you've got regular Coke, which is here. That's mu2. We want to test this claim. Test a claim that the contents of cans of Diet Coke weigh less than the means, excuse me, let me try this again. The contents of cans of Diet Coke have weights with a mean that is less than the mean for regular Coke. So, okay, they're giving us a claim to test. How would you write that claim in terms of symbols? What would that look like? We're going to use mu1 for Diet Coke, mu2 for regular Coke. So what would that claim look like in terms of symbols?
Mu1 is less than mu2?
Yeah, mu1 is less than mu2. So there's your original claim. See which one of these four, and I'll label them here. We'll call them 1, 2, 3, and 4. Which one of these we can, claim as our own for this particular hypothesis test. By the way, no, this isn't as standout as, yeah, there is one here. What's one of these that I could just look at and say, no, this one can't be right, without even reading the problem? Royale?
3.
Yeah, 3. Good. Why?
Because it says not equal.
Exactly. We can get rid of that one right away because your null hypothesis has to have the possibility of equality. So that one's just clearly wrong at the start. Look at the remaining 3 and decide which one you like. Carly, which one's looking good here?
Number one.
First one's looking good?
Yeah.
All right. Yeah, that one's looking good. So let's take a look here. So this would have to be part of an alternative hypothesis, and I see that alternative hypothesis here. And the other two alternative hypotheses don't match this, so yeah, good job, number one. So there's your first step. First step is to state the null and alternative hypothesis. Second step is decide on the significance level. And I hope that you start getting used to this pattern of 6 different steps. So there's step 2. What's step 3 been for us? What have we done in step 3? Input the data. So the data is actually given to us in the form of summary statistics right here. Let's take a look at inputting that into StatDisk. So open up StatDisk, and let's see if I got any data here. I'll just go clear that out. Not that I really am worried about that in this particular one. Where do you think I should go to try and decide this, do a hypothesis test for this one? Well, in StatDisk, where do we typically go? What gets most of our work done in StatDisk? Analysis. And then it looks like we're doing a hypothesis test. I've got 7 choices here. Which one looks right? Mean 2 independent samples. So let's choose that one. Now we're going to input our summary statistics. We don't actually have the raw data itself. If we did, we'd have to click over here. The first box down there, we have to check what's our alternative hypothesis, 1, 2, or 3. What's looking good there? 3 is looking good. So we got mu1 is less than mu2. Let's see. We had a 1% significance level, so I'll throw that one in as well. Now these numbers are kind of, not terribly fun. So let me kind of look back at these here. So we got 30 sample size of 30 for both of these. X bar was 0.78344 and 0.0047. So let's put those numbers in. So 0.78344. Whoops, that's wrong one. Let's just copy this though. Our sample size was 30. Sample mean was this. Sample standard deviation was 0.0447. Let's just double check that. Yep. Sample size here, again, 30. This time the mean is 0.8 something. 0.80501. And finally 0.00758. Nice. Typically speaking, you should not know what sigma is here. I can't, like I said, realistically think of a case where you know the standard deviation and not the mean. We're going to assume that we have unequal variances. Now, if for some reason you can assume that you have the same standard deviation for both of these, you get a slightly more powerful test. That means you're a little bit more likely to be able to reject H0 when it's false. So probably best not to change this. We'll leave that set as it is. Click evaluate, and let's see here. Nice. What do I need from this step? Yeah, the p-value. And the p-value is a big 0, right? So step 3, step 4, the p-value equals 0. You can put 0.0000, that's fine. Doesn't matter. Doesn't change our conclusion. What are we going to conclude in step 5? What should I write there? What do you think?
If it's, the p-value is lower than we reject.
Okay, so what's that leave us to do here? Our p-value is 0, our significance level is 0.01. Awesome, thank you. Reject H naught. If the p-value is low, H naught must yawn. Oh, that is go. No worries. All right, let's take a look here. You've got several different choices for wording your null hypothesis. Did our null hypothesis, or excuse me, wording your conclusion, did our null hypothesis include the possibility of equality? No, did not. So we're okay there. That moves us down here. Did we reject the null hypothesis? Yes. So we're going to use this to write our conclusion. Now, in writing your conclusion, when it comes to the original claim part, you could just use the original claim from right here. You don't have to be wonderfully creative. Sometimes I am, sometimes I'm not. But in our case, they've given you several different conclusions that you can choose from. Which two can you get rid of right away? Yeah, A and C. Matt says A and C. He's exactly right. Why can you get rid of those right away? Yeah, it says fail to reject, but we rejected. So let's get rid of those right away. That one and that one. Of the two remaining, which one's looking good? Yeah, B is looking pretty good. Let's take a look at D and see what might be wrong with that. Reject the null hypothesis. It says there's not sufficient evidence to support the claim that cans of Diet Coke have mean weights that are lower than the mean weight of regular Coke. That's not true. That's not what we concluded. We concluded that there was sufficient evidence to support the claim that cans of Diet Coke have a mean weight that is less than the mean weight of regular Coke. So, yeah, this one's our winner right here. All right. Looking good on that one. Let's stick with this one a little bit more because there was something on the exam that I saw that I'd like to help you correct. So, not everyone, but you know, enough. Let's take a look at our null and alternative hypothesis again and kind of play around with things a little bit. We've got a confidence interval for the difference in the means. And that's actually given to us here, although it's not quite the confidence interval that I want. What's wrong with this in terms of it being a good confidence interval matching my value of alpha? Yeah, we got a significance level of 1, so this plus this should be equal to 1, and it's not. It's off. Now, there's two workarounds that you can use for this. One of them is you could change that to half of what it was. If I redo my interval, I should get a 99% confidence interval. The other possibility is you can leave that the same and just change it to a two-sided alternative. That is a two-tailed test. So that's looking good. And when I hit the evaluate button, I get the same thing as before. But the important thing is I've got a 99% confidence interval, and that matches my significance level. So I like it when I got that nice match. Now, let's write down this, and I think I'll round this to the nearest thousandth. So negative 0.026 and negative 0.017. So negative 0.026 less than or equal to mu1 minus mu2 less than or equal to negative 0.017. And I think that was in units of pounds. So, okay. In words, you would write something like this. we can be 99% confident that the true mean difference, and here it's not a bad idea, it's kind of polite to your reader to mention which way you're subtracting things. In this case it'd be diet minus regular is between negative 0.026 and negative 0.017 pounds. So it's a nice statement of what this reflects. What's one of the important words that I like to see in this statement? Thank you. The word true. All right, so the word true, looking good there. That's kind of like a subtle, sneaky way of saying parameter. Now, most people, if you read this, if they haven't taken a statistics class, they're not going to know what a parameter is. So by saying the true mean difference, we're really hinting at the parameter without saying as much and keeping it a little bit more user-friendly. As far as the hypothesis, or excuse me, the confidence interval is concerned, does this match our conclusion from our null hypothesis? This is the point that I wanted to get to. It was a little bit of a sticky point on the exam. Let's take a look at our null hypothesis. So I have H naught such that mu1 equals mu2. What if I subtracted something like mu2 from both sides? What does that give me? What's my new alternative or my new null hypothesis looking like? Somebody give me the right-hand side. 0. And on the left-hand side, are these like terms? No. So it's just going to be mu1 minus mu2 equals 0. So is it fair to say that both of these things are equivalent? That when this one's true, or vice versa? Okay. Let's look back at our confidence interval. The important thing to see is that both of these terms have the same sign. That is, they don't include 0. Now, if this was true, or this is true, then this confidence interval should contain 0. It should contain that possibility. Because it doesn't, well, you're starting to doubt H1 could be, or H naught could be true. If H naught was true, 0 should be one of these possibilities. But it's not. And since this doesn't contain 0, you would tend to reject H naught. That's the conclusion that you're getting from this. So that we rejected H naught here and that our confidence interval does not contain 0, those two things match. Those two conclusions point in the same direction. Now, if on the off rare chance these things pointed in different directions, which one do you go with? Do you go with the hypothesis test or the confidence interval? What have we said in this class? Hypothesis test. Now, it's probably not going to happen very often, if at all, for you, but if it does, go with the hypothesis test. Nice. That's a good one. This is a real good example to start things off with. We okay with that one? Is there any follow-up on this one? There's a lot of discussion here. It took us the first half hour of class. Yes?
Can you like go over the last one again? I didn't quite understand like the whole.
Sure. I'm just reshuffling this by subtracting mu1 or mu2 from both sides. So mu2 minus mu2 gave me 0. And over here, because these aren't like terms, it's like an x and a y. It's just mu1 minus mu2. But what it's saying is that the difference here, if this difference is 0, that's equivalent to both of these being equal. The only time that you could subtract two things and get 0 is if those two things are equal. And so that's the importance of this part, is recognizing that when the difference is 0, those two things have to be equal. They're just saying the same thing. So the importance of that is it allows us to really understand this confidence interval a little bit better. This confidence interval says the difference in these two is going to be negative, meaning that when you subtract the weight of regular Coke from the weight of Diet Coke, this one's going to be more, and you're going to get some negative value. That's why both of these are negative, is because, yeah, that difference is somewhere negative. These tend to weigh more than these, is what it's saying.
So is that to test whether the confidence interval matches with the claim?
Yes,
Oh, okay.
it's exactly right. So it's exactly to show that our conclusion here and our conclusion here match each other. Now, a lot of times, if you were doing this on an exam, for instance, and you wrote mu1 equals mu2, I'd be really happy with it. No problems. That's fine. But statists sometimes, depending on the problem in particular, it might think of things this way. And it's just going to give you a confidence interval for a lot of these things that is reflected by this. Appreciate the question. Thank you. Okay, let's flip it over. So now we're going to talk about samples of hemoglobin. What does hemoglobin do for you? What's that? It's in your blood. It carries oxygen, right? Definitely want high levels of hemoglobin, unless you like gasping for air. In any case, large samples of women and men are obtained, and hemoglobin levels obtained as measured in each subject. Here's a 95% confidence interval for the difference in the two population means, where measures from women correspond to population 1 and measures from men correspond to population 2. So if you don't want to use mu sub m and mu sub f, then something like this is appreciated, telling me which population is which. What does the confidence interval suggest about the equality of the mean hemoglobin level in women and men? So basically they're asking you, what would it say if you were doing a hypothesis test of mu sub 1 equals mu sub 2, would you be rejecting H naught? And what you want to look at is the confidence interval. By the way, in case you're curious, the units here are grams per deciliter. So, you know, not exactly a common unit for us, but that's okay. Grams per deciliter. A gram is really, really small. A paperclip weighs about 5 grams. So if that gives you a little hint as to what it is. There's 28 grams in an ounce. But in any case, what does the confidence interval say about the equality of means hemoglobin levels between men and women? So are you going to reject H naught or fail to reject H naught for this problem based off this confidence interval? Colin's saying reject H naught. Let's see, Nick's agreeing. All right. Why? Why are we rejecting H naught? Doesn't include 0. So this is equivalent to mu1 minus mu2 equals 0. 0 is not in here. So this nor this could be a possibility, at least according to our confidence interval. So yeah, you're going to reject H naught. And that's going to correspond to this. Well, this is their way of writing this. I would say that we can be 95% confident that the true difference in hemoglobin levels, and I assume it's women minus men, is between these two values, etc. But the big thing here is that we're going to reject H naught because this confidence interval does not contain 0. Okay. Are we feeling a little bit better about this one and this idea of rejecting or failing to reject if 0 is in your confidence interval?
What does it look like when when there is 0 random like that?
If the 0 was in our confidence interval, then we would just fail to reject. So,
I'm just confused on student equals.
well, here, let me give you an example of a confidence interval that would contain 0, maybe negative 0.96 grams per deciliter is less than mu1 minus mu2 is less than 1.38 grams per deciliter. So the big thing is that you'll see a change of sign. It'll go from negative to positive. So this contains 0 because it has a change of sign. So this would be a fail to reject H naught. Appreciate the question. Anything else on this one? All right. Thanks for the question. Let's see. Listed in the data table are the amounts of strontium-90, which is a radioactive, in millibecquerels or MBQ per gram of calcium in a simple random sample of baby teeth in 2 cities. Now those 2 cities are Chicago and Detroit. Certainly you don't want to be on the bigger end of this because we don't want radioactive teeth. Assume that the 2 samples are independent simple random samples selected from normally distributed populations. Do not assume that the 2 standard deviations are equal. Use a 10% significance level to test a claim that the mean amount of strontium-90 from city 1 residents is greater than the mean amount from city 2 residents. So that stuff is right here. Let's start by writing, an original claim. What would that look like? We're not going to worry about the null and alternative hypothesis just yet, but just write our original claim in terms of mu1 and mu2. Now, a lot of times I would write mu sub d and mu sub c for problems like this, but I don't know. Seems like there's a preference for mu1 and mu2, so we'll stick with that. Amelia, what's our original claim looking like? What do you think we should write? Yeah, mu1 is greater than mu2. Cool. Nick, I. Is this going to be part of our null or alternative hypothesis? Yeah, the alternative hypothesis. Good. So that has to correspond to this one over here. Let's see, mu1 is greater than mu2. Certainly we can get rid of this one right away, right? That doesn't have the possibility of equality in the null hypothesis. What else? This one's got the wrong alternative hypothesis. And this one I would actually accept. I'd be okay with it on the exam. I think they're looking for this one because my StatDisk just doesn't do this. So this is okay for Jeff Parent. But this is, I think, what they're going to be looking for. StatDisk and the author, I don't think, really use this like I do. So that's okay. Let's throw some data into StatDisk and see what we can come up with. There should have been a link for you in D2L to the data set. So you want to find that link, you can go to content and then links to data. Should be like the last one down there. Open that up. It should open up to this right here. Nice. Just grab that data. Don't grab the Detroit and Chicago part of it because StatDist doesn't like things other than numbers. If you have some data there already, hit the clear button. If not, you're good to go. Just paste it in and we're ready to do our analysis. So the first step was our null alternative hypothesis. That's here. There's our first step. Our value of alpha in this case was kind of on the large side, 0.10. Typically, I've only seen that in the classroom. Once you leave the classroom, the largest value of alpha that I've seen is 0.05. I've never seen somebody use a 10% value for alpha. Third step is to input our data. All right, we've got that all done. So then the fourth step, we need to figure out a p-value. If I remember this problem correctly, I think I know why they chose alpha's 0.10. Analysis, hypothesis testing, mean, 2 independent samples. And we're going to start this one a little bit differently than we've started our other ones. What's different about how we're going to work this problem?
Use data.
Yeah, we're using data, right? We're not using summary statistics. We don't have X bar and S calculated for us for these, so that's okay. Which alternative hypothesis do I want to use? 1, 2, or 3? 2. Yeah, we want the first population as a mean that's greater than the second population, that is Chicago's bigger than Detroit. All right. And let's see, let's make that 0.10. Data from column 1 and column 2 respectively. You shouldn't be plugging in anything for standard deviation. We don't know those. Let's keep it as unequal variances. And bam. All right. So our p-value is 0.0653. All right. What decision does that give us? Safe? What are we going to do here for step 5?
P-value is less than alpha.
Therefore, what?
Reject H now.
Awesome. Reject H naught. Perfect. Perfect. So here's your original claim. Let's take a look at which form of our conclusion that we're going to make. Bless you. So you got 4 choices, A, B, C, or D. If you're watching this at home, try and make your choice. If you're here, make your choice and then compare it with the neighbors. Which one do you think here? Okay. Does anyone want to give this a shot? Want to check out your wording? Got something? Garrett, you look proud of yourself. Go ahead. Give it a shot. What do you got? All right. Agree. Choose C. We didn't have equality in our original claim, and we rejected that. So, looking good so far. Strontium. Strontium. Yeah, there you go. Cool, cool. All right. Mine's pretty similar. The sample data support the claim that the mean amount of strontium-90 in baby teeth from kids from Chicago is greater than the mean amount for kids from Detroit. So, yeah, pretty similar. We're saying the same things. You don't have to use the word true in stating your conclusion for a hypothesis test. True is only something I need to see for confidence intervals. Now, in fairness, I'm not really sure we should be doing this test. And that's because the data have to be normally distributed in order to do this test. How can we check and see if the data is normally distributed? We should really have done this beforehand, but I'll explain why we didn't in just a minute.
Histogram.
All right, we can do a histogram. Good. And in fact, we can do a really nice complete job if you go up to the data menu and you click normality assessment. Which one do you want to assess? Well, let's try the first data set. And here's your Ryan Joyner test. It says reject normality at the 5% significance level. It's like, you know, at the 5% significance level and the 1% significance level, this doesn't look like a normal data set. Let's actually scroll down a little bit. Here's your histogram. Does that look like it's normally distributed? What should it look like if it's normally distributed? Yeah, bell curve. Ew, not looking too good there. How about over here? Here's your normal quantile plot. Does that look good there? No, it looks even worse over here. So not looking so good. So I kind of think that we shouldn't have done this. Now I think the data from Detroit, if you click that column, then at the 5% significance level you can reject, not at the 1% significance level. If you want to raise that standard up to 1% significance level, and the data from Detroit doesn't look as bad, all right, it looks a little bit more normal, but you know, really it's tough to say with 12 observations if it's normally distributed or not. We'd like to have more. The reason we could get away with going ahead here is that they actually say in the problem, and I didn't actually catch this in my morning class, that assume that they have simple random samples from normally distributed populations. So that gives you license to go ahead and do the test. But without this, then you shouldn't be doing the test. So without this assumption, you shouldn't do the test. At least this way. All right. There are other ways to do these kinds of tests. There's a method called bootstrapping and other non-parametric ways to do these kinds of tests. But, well, you know, we were told to assume that the samples were simple random samples from a normally distributed population. So, okay. So we're all right doing our test, but in my mind, should probably be looking at that thing ahead of time and going, yeah, it doesn't look like it's normally distributed. Okay. Comments or thoughts on example C here? All right then. That's it for section 9.2.